Fetchers of America, welcome back to another episode of Brother Rich TV. We're going to complete our factoring methods today. I want you to do something right now. I've asked you to do it every time for the last few lectures. Let's go ahead and on your notes, let's write the 5 methods of factoring and the type of polynomial they are possible on. We'll pause for a minute. Go ahead, Alan. All right. So you wrote these down. There are your 5 methods of factoring. We are going to do the last one today. Can you see me in the camera, Hallie?
Yep.
All right, good. Okay, so we've learned how to pull out a common factor, how to factor 4 terms by factoring by grouping. Every polynomial has the potential of having a common factor. We learned the 2 trinomial methods. You're never going to use both. It's either one or the other based on whether A, the lead coefficient here of the degree 2 term equals 1, or A does not equal 1. And then today we have to learn about special cases, okay? So let's go ahead and pause again, Helen. Okay, guys, I want to really try to help you be efficient. And so the next thing I want you to do is I want you to write this chart down in your notes right now. So you did this, and I want you to write this. Before I pause and have you do it, I want to tell you, notice that this says special cases. Cases. Yeah, that's right. Okay, so it means it's plural. So there's more than one. I often ask students, how many special cases are there in algebra? And I could say, well, I'm looking through the camera, I see about 25 of you. Okay, cool. That's funny, huh? All right, of course, we're all special cases in one way or another. But in algebra, there are 4 special cases. There's what's called the sum of squares, the difference of squares, and then there's also the sum and difference of cubes. So the sum of cubes and the difference of cubes. This is beginning algebra, so we do not learn all 4. We just learn the sum of squares and the difference of squares, and we save the sum and difference of cubes for the future for you. If you take intermediate algebra, you'll learn that topic. So let's go ahead and pause and have you write this down. 1, 2, 3. Hallie's doing a fantastic job of running the camera today. You want to pop over here again, Hallie? Yeah, come on, come on. Wave to the camera. Got the curls, the girls with the cute curls. This is Hallie. She's my youngest. She's the best. Yeah, we love her. Okay. She's tired. It's Saturday night. And you guys, yeah, we're working on a Saturday night for you to make it happen. Check it out. So, how'd you write all of that down? And now I want you guys to do something interesting here, okay? I want you to join me on a little journey. So this is all this knowledge you need to know. First of all, the sum of squares is always going to be 2 terms that are perfect squares being added, or the difference of squares, 2 terms that are perfect squares being subtracted. When you try to factor this one, the answer will always be prime, and when you factor this one, it'll always be a plus b times a minus b. An example here, x squared plus 4. 4 is a perfect square. X squared is a perfect square. Okay, but the answer is prime because they're being added. Here we have x squared, that's a perfect square. 4 is a perfect square, but they're being subtracted, and so the answer is x plus 2 and x minus 2. We'll talk about how to arrive to that answer. That's what we're going to learn how to do today. Okay, but before we get into that, I want to talk to you a little bit about perfect squares. So the first thing I'll need you to do is I'll need to have you get your calculators out. So go ahead and get your calculators out, and I'm going to have you guys help me for just a minute. First thing I want you to do is I want you to tell me what are the first 12 perfect squares numerically. So when we talk about numbers, I want to know what are the perfect squares. The first one is 1, okay, and the next one is 4. If you guys can join me on this, the next one is 9. Then 16, then 25. Hallie, do you know? This is kind of tough. There's a little pattern involving here. 36. 49. Okay. 64. Do you know? 81. All right. Guess. Guess. 100. Okay. I got to write it up here now, the next couple, 121 and 144, okay? Now, why are those the first 12 perfect squares, okay? Well, if we take the square root of this, it equals 1. If we take the square root of 4, it equals 2. Square root of 9, it equals 3. Square root of 16, it equals 4. Square root of 25, it equals 5. Square root of 36, it equals 6. Square root of 49, it equals 7. Square root of 64, 8. Square root of 81, 9. Square root of 100 equals 10. So you start to see the pattern here. Okay, square root of 121 equals 11. Square root of 144 equals 12. Okay? You need to memorize the first 12 perfect squares. You need to know that these are perfect squares, okay? I mean, you don't need to spend hours figuring this out. I'm just saying you need to know that all of these numbers are perfect squares. I'm going to talk to you about this here in a minute. Next thing I want you to understand here, and again, you've got all this written down and all this written down because we're going to have to erase some things eventually, but I want you to look at this right here. We just took the square root of stuff, okay? If you're not really familiar with this, arithmetic principle, I mean, everybody's probably worked with this at one time or another, but this is what we call, a square root, okay? But the reality is that this is really called a radical expression, okay? This is really called a radical expression. Because if we look at the anatomy of this whole bar is called the radical bar. Totally radical, okay? I grew up in the 80s, so, this is our language back then. Okay, so this is the radical bar. This portion right here, and by the way, you're not going to get tested on this, but this is interesting knowledge, and it's important that you know this, okay? It's not critical that you understand this. It's not going to be on the test, but I do want you to understand this in math. Okay, this is called the caret. Okay, not C-A-R-R-O-T, like the one you eat. Watch out, Doc, right? I know, it's terrible dad jokes, but Hallie's laughing, so we're all happy about that. Plus the bunny farts with jokes. Some of you got that, I heard, and that's good. Okay, and inside the caret, there's always inside here, there's a number, okay? And if there's no number written, then we always know it equals 2. And that's why we call this the square root. But I do want you to know that the radical bar is just like the laws of exponents. It's a shortcut. Okay? And it's a shortcut that asks a question. Alright, so this board's getting a little bit messy here. It's not like when we're in the classroom, we have 3 boards and I can go crazy on it. So I am going to erase this up here. You keep that in your notes, you've got that, okay? But I am going to erase it just to give us more space. And you were asked to write that down, so if you didn't, you can pause, go back, write that, whatever, but you'll need to reference that. We're going to use that, and I'm not going to rewrite it up on the board for you. I'm going to assume you have it next to you so that we can reference it, okay? But the thing I want you to understand about a radical expression, okay, so this is what we call a radical expression. I told you that these are shortcuts. And the shortcut asks a question. It's asking the question, what number times itself the number in the caret, okay? And by the way, that number, it's called the root, okay? So what number times itself the number in the caret, which is the root, okay, equals the number under the radical bar. Alright, so we think about this. If I take the square root of 16, alright, what's inside there is a 2. Because we said if there's no number written, it's always a 2. Okay? And so the square root of 16 is asking the question, what number times itself equals 16? Well, it's 4. Because we know that 4 times 4, here's the answer 4, equals 16. What number times itself 2 times equals 16. So think about this. I could take the third root of 8. Yeah, I can put a different number in there. So if it's not written, we know it's a 2. But if we want to write another number inside the caret, we can have another root here. So the third root of 8, okay, the answer is 2. Why? Because 2 times itself 3 times, right? What number times itself 3 times, okay, so this is our number here, equals the number under the radical. 2 times 2 times 2, that's 3 times. 2 times 2 is 4 times 2 is 8. It equals the number under the radical, okay? And so we can do this stuff. In fact, we can take the fourth root of 16, okay? That's an interesting one, all right? The fourth root of 16, that equals 2 as well. Okay, why? Because you take what number times itself 4 times 2 times 2 times 2 times 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. What number times itself 4 times equals 16? It's 2, okay? So in this class today, all right, I wanted you to understand that because you're moving on. You know, I mean, we got a week left of school and you're moving on. You're moving on to collegiate level math. And you need to understand radical expressions, that they're just simply shortcuts. They're asking a question. What number times itself, the root number, equals the number under the radical? Okay? That's what we're asking you. Okay? Just going to erase all that. And I just want you to understand that as far as this class is concerned, okay, we're just going to be talking about square roots. We're not going to worry about the third root, and the fourth root, and the fifth root, and all that crap. Okay? We're just sticking with the goods, the square root. Okay? Keep it simple. All right. Hopefully you're able to read everything that was on that board. I didn't check on that. We kind of wrote out there to the edge. You keep an eye on that for us, Hallie, will you, Camera Girl? Yeah, Camera Girl. I think there's a song about Camera Girl. Okay? We'll have to make one up if there's not. Okay? So there's our first 12 perfect squares numerically. Okay? 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. So when we see those numbers, we need to be able to recognize that they're perfect squares. What about in the variable realm? Okay? So these are numerical perfect squares. These aren't all of them. I mean, there's obviously an eternity of them. But I want you, before we go into the variable realm, I want you to understand what a non-perfect square is. Okay? A non-perfect square. Okay? So I'm going to have you pause for a second, but I want you, before you pause, I want you to take the square root of 5, okay? Let's go ahead and do that. Let's hit pause. We're back. Okay, so you took the square root of 5. Okay, Hallie, what do we get when we get the square root of 5? Go ahead and read that to me.
2.230606 7977 49979.
Wow, that's a lot of digits. And for those of you at home doing this, you probably didn't have that many digits in there. You probably had less than that. Now, I want you to do something right now with me, okay? And Hallie, you do it too. So I want you, did you clear it? Don't clear it. Leave it on there, okay? I want you to hit times. And then I want you to type this in, okay? Go ahead, 2.236797749979. And for those of you at home, if you ran out of space, just go as far as you can, okay? And hit equals. What do you get?
5 point, a lot of zeros and then 1.
Okay. So Hallie reveals to us that she got 5.0000000, and she said a lot of zeros, and then 1. Okay? And so what I want you to understand is that these are called perfect squares because when you take the square root of them, you get an integer. But when you take the square root of every number in between, like in between 1 and 4 is 2 and 3, and in between 4 and 9 is 5, 6, 7, and 8, between 9 and 16. So I knew that 5 would be 2 point something because it's got to be between 2 and 3, okay? But here's the deal. There is no number times itself that makes 5. This is why this is called a non-perfect or an imperfect square. You can take this. See, this number is, if you remember, it's an irrational number. Remember the irrational numbers back in the first, well, it was chapter 1, which was on our first section of chapter 1, we talked about all the different number sets. And so this number goes on forever and ever and ever and ever and ever, but it's unpredictable. There's no pattern to it. And the more digits you press in, the further the zeros go until you hit 1, but it's never 5. It's trying really hard to give you what you want, okay? Because there's a little bit of artificial intelligence in your calculator, just a tiny bit, and it wants to give you what you want because it knows that you're trying to achieve 5, but there is no number times itself that makes 5. So when you take the square root of it, you're asking it to do something it can't, and so it's taking it as far as it can to get you there, okay? That's kind of a cool concept. So what about variables, all right? What about variables? So is x squared a perfect square? Okay, well, sure, because if we take the square root of x squared, it equals x. What times itself 2 times, because we're just doing the square roots, equals x squared. Well, x times x equals x squared, so, it is x, okay? Well, what about x to the 4th? Okay, well, the square root of x to the 4th is x squared, right? Because x squared times x squared equals x to the 4th, right? Okay, what about x to the 6th? Okay, somebody said, no, it's not. It is. Okay, why? Because it equals x to the 3rd. Notice we have x to the 1, 2, 3. It's going to keep on going here. And why is this? Because x to the 3rd times x to the 3rd. If you remember your laws of exponents, we don't multiply 3 times 3 and get 9. We add them, right? Because little numbers and big numbers behave differently. We've talked about this as they should. And so this equals x to the 6th. And so we see a pattern develop here that every even exponent is a perfect square. And so we can write that up here. Every even exponent, okay, equals a perfect square. All right? Every even exponent equals a perfect square. All right? So, again, I'll ask you, is x to the 3rd, so we go back to the non-perfect squares, is x to the 3rd a perfect square? So we take the square root of this. Well, is there something times itself that makes x to the 3rd? And you could say, well, x to the 1.5 does. Okay, but that's a decimal, right? And because really, if you took x to the 1.5 and you squared it, okay, which would be x to the 1.5 times x to the 1.5, you get to add those two and it would be x to the 3rd. But it's a decimal, and you have to have, you can't have a decimal, okay, or it's not a perfect square. So the point being that the odd ones, okay, all right, it's just not going to work, okay? There is no perfect square to your odd exponents. So there's no square root of x to the 3rd, there's no square root of x to the 5th, okay? There's no square root of x to the 7th, or to the 9th, or to the 11th, or to the 13th, okay? Because you got to be even to have a perfect square. Now, if I asked you what was the 3rd root of x to the 3rd, well, that would equal x, because we would be asking what times itself 3 times equals x to the 3rd, and so that would be true, okay? All right, so right now, all I've done is I've established what perfect squares are, and you'll see why it's really important, because you're going to need to be able to identify what a perfect square is. So let's pause real quick. Okay, guys. So today's lecture, I need you to really stick with me, because a lot of times I teach you a simple concept, we have a set of steps, and then I teach you, how to implement those steps on problems. And we're going to get there, but I've been going through some things with you, all right? First of all, reminding you of our 5 methods. Second of all, identifying what special cases are. Still haven't taught you how to even find them, but gave you a little chart about the sum and difference of squares. And then third, I talked to you about radical expressions, okay? And so you understand what a radical bar means. It simply asks the question, what times itself equals the number, okay, under the radical bar, or the expression under the radical bar. And then I taught you about perfect versus non-perfect squares and how to identify them. Let's go ahead and let's join each other. I want you guys right now, just in a little bit of review of things that you've done. I've left this on the board purposely, and I want you to factor these 2 problems, okay? So I'm going to give you some hints before we pause. Hallie's ready to press the pause button, aren't you, Hallie? Yeah. Okay. And so, but we're gonna give you guys a couple minutes to do this. But before you do, I just want to tell you, you need to approach every problem as you are a cancer doctor, right? And we're trying to pull all the cancer out of these patients so they can live a healthy and long and productive life. And you are going to have a test on chapter 5, and this is the reality, is that, we learned how to do this method in section 5.1, and this one in 5.1, and then this one in 5.2, and then this one in 5.3. We're skipping 5.4. We talked about that because we got rid of the trial and error method of this, and this one we're doing 5.5. But the reality is when it comes to taking a test, there is no 5.1, 5.2, 5.3, 5.4, 5.5, and all that crap. It's just polynomials that need to be factored. And you need to approach it from all of this. So that's why I keep having you write this down and memorizing it. So make sure you check for common factors. Make sure that you, look, do you have 4 terms? Can you factor by grouping? 3 terms, you know, do you have a equals 1 or a doesn't equal 1? We'll give you a minute. Go for it. All right. Hopefully you guys nailed this, okay? So when you looked at this one, there was a common factor, okay? So we've got 8, and 8 goes into 16, but 8 doesn't go into 2, but 2 goes into 8 and 16 and 2 and 4. These are all even, so they're all divisible by 2. So we have a common factor numerically of 2. We have an x, an x, an x, and an x, and that's the lowest degree of the common variable. And so we have a common factor of 2x. So you should have put this over 2x, and put this over 2x, and this over 2x, and this over 2x. And then you should have had 4x to the third minus 8x squared minus 2. No, those cancel. X squared over x is x, and 4 divided by 2 is 2, and the x's cancel, and you have these 4 terms, and the 2x goes right there because you pulled out the common factor. Now, if that's all you got, you didn't get it right, because you have 4 terms here, and we have to approach this as a process, okay? So we pull out a common factor, and now we check to see, can we factor by grouping? So we're going to drop this down here, call this 2x, and then we're going to say, all right, we're going to reorganize this, 4x to the third minus 8x squared, put it in a binomial plus negative x plus 2, put it in a binomial, always put a plus in between these, a bi plus a bi, pulling out the common factor here, 4 goes into both 4 and 8, so we have 4, x to the third x squared, lowest degree of the common variable is x squared, so we put this over 4x squared, we put this over 4x squared, and we get x minus 2, okay? The x squareds cancel, negative 8 divided by 4 is negative 2. Now, look at this. There is no common factor there, and we have an x, and we have an x, we have a 2, and we have a 2, but this is a positive, a negative, that's a negative, a positive. And so we said we don't want to give up easily in factoring by grouping. We need to pull out a negative 1. So we should pull out a negative 1 here, put this over negative 1, put this over negative 1, and we get positive x minus 2. Okay? So hopefully if you didn't, hopefully you got the common factor. If you didn't, you should pause, go do that. Hopefully you factored by grouping. If you didn't, you pause, you go and you check that out. Now, the common parentheses is x minus 2. And the leftovers go in this parentheses, 4x squared minus 1. All right? Now, if you got that, okay, clap your hands, woo, give yourself a woo. Okay, say woo, Hallie. Woo. Yeah, woo. Okay, we got it, and we're feeling good. But guess what? This isn't the final answer because of special cases. And this is what I'm going to talk to you about right now, ever so briefly, okay? So let's take this up here. We're going to hold off on that one right there, put a little wavy thing there. We'll come back to that problem in a second here. But we have 2x times 4x squared minus 1, and we have x minus 2. All right? So I'm going to teach you this concept as we go here, but I want you to see the answer to this problem is actually 2x times 2x plus 1 times 2x minus 1 times x minus 2, okay? And that's the final answer. If you were taking a test, that would be it. And what you would have done in this is you would have pulled out a common factor, factored by grouping, because you had 4 terms, and it succeeded, and the trinomial methods are out because there's no trinomial, but then every binomial has the potential to be a special case. And so you have a binomial here and a binomial here. And that's why we say this for last, is that, you know, you can have a binomial and you have to factor it, but a lot of times at the end of a problem, you have binomials as part of your answers. So let's look at this right here. So this is not a binomial, it's a monomist. It's coming along for the ride in the answer. But I want you to see what I'm going to do, and I'm going to write all this down for you in a little bit here. But check this out. Is 4 a perfect square? Yes, it is. Is x squared a perfect square? Yes, it is. Is 1, not negative 1, 1, is 1 a perfect square? And some people say, no, what's the square root of 1? 1, it is a perfect square, okay? So all of those are perfect squares. Now, is x a perfect square? Nope, because it's x to the first. We said odd exponents, not going to happen. Is 2 a perfect square? Nope. And so that comes along with the answer. But because all of those terms were perfect squares, all of them were perfect squares, we have to do something. So what we're going to do is we're going to take the square root of 4, and that's going to make 2, and the square root of x squared, and that's going to make x, and the square root of 1, and that's going to make 1. And those two terms are going to be put in a sum and put in a difference, okay? Now, Hallie, I want you to sing this with me, okay? You got to do it. We got to be cool, okay? We're going to sing. But listen. I want you to take your hands and I want you to stir them. Yeah, I wish you guys could see Hallie. She's stirring it, okay? Okay? All right? I want you to stir it. Yeah, and as you stir it, I want you to say, put it in a sum.
Put it in sum.
Put it in a difference.
Put it in a difference.
Now let's put it all together. Put it in a sum. Put it in a difference. Okay. And the only reason I do that is it helps you memorize it, all right? So what we did is we had all perfect squares here. And because we had all perfect squares, we have a special case. This is the difference of perfect squares. And so when we do that, we take the square root of each term. Square root of 4 is 2. Square root of x squared is x. Square root of negative 1, or 1 is 1. And then we'll put those two in a sum of those terms and put those two in a difference of those terms. Now, right now, you're like, oh my gosh, Brother Rich, you're not writing all this down. You're just telling me. I just want to show you where we're leading this discussion today. So, we're going to go ahead for a second before we move on, and we're going to pause in just a minute. I'm going to erase this problem, okay? And then what I want you to do is I want you to look at the problem you just did here and see if any of your binomials are perfect squares. And while you're doing that, I'm going to write down these steps that I just talked to you about, okay? Let's go ahead and hit pause, Hallie. Okay, guys, we've been working while you've been working. You can see here on the board. I hope you can see this. Sometimes when I reformat the videos that we take, just so that we enhance the lighting a little bit better, different color pens don't really show. Hopefully you can see this in the red pen here. Let's go ahead and let's do this problem, and then let's apply this where we can, and then we're going to do some other problems using this, okay? So we have b to the 4th minus 18b squared plus 81. We first check for a common factor, because we always do. We have a b, no b. We have no numerical common factor, so we do not have a common factor. We do not have 4 terms, we have 3 terms. If we have 3 terms, we know we have a choice between one of these two methods. We're choosing here whether a equals 1. And Hallie, can we see all this in the camera, everything in here? We all good?
Yeah.
You see all this, okay? So a equals 1, or a doesn't equal 1. So let's come back to this. Remember, a is the coefficient of the first term. So what does a equal here, Hallie? There's a 1 there. A equals 1. What does b equal? Negative 18. What does c equal? 81. Hallie's in grade school, guys. She is killing it. She does pretty good here, but she's like, what's up, Doc? Yeah, absolutely. Okay. So check it out. If a equals 1, we're using method 3. And we learned that we're going to make a chart here of c equals 81 and b equals negative 18. And so we want to find two things, multiply together, make 81, when add together, make 18. We know 9 and 9 make 81, but they make positive 18. Negative 9 and negative 9 will make positive 81, but when added together will indeed make negative 18. There's our magic pair. And so then we learned that this is super fast. We need this term and this term to equal that term. So we're not going to have just x and x because they're b's, and we can't have b and b because that would make b squared. So we have to have b squared, which makes b to the 4th. And then it will be minus 9 and minus 9. Agreed? Okay? Because there's our magic pair. And they go down there. And normally, from what we learned before today, we would think we were done. But if you examine these binomials, you go through this kind of process here. And I am going to have you write this down, but it's going to be pretty easily memorized. I don't think you're going to need to spend a lot of time figuring this out, okay? So the first thing we do is we say, do I have a binomial? Because if you don't have a binomial, because this is our special case inventory, basically we're checking, do I have a special case? You know, the special ace, there we go. Do I have a special case? Okay? And if I have a special case, then I have to determine, you know, is it the sum of squares or the difference of squares? Because the sum of squares is always prime. That was our first chart. Where the difference of squares is always going to be put in a sum and put in a difference, okay? So we come here. Do I have a binomial? Yes, you have two binomials here in your answer, okay? If the answer is no, you're done. You don't have a special case. If the answer is yes, then we move on to the next step. Are all the terms, all parts, both coefficients and variables, perfect squares? And so we come here, there is no coefficient except one, and one is a perfect square. So b squared, is b squared a perfect square? Yeah, we talked about that. Any variable to an even degree is a perfect square. Is 9 a perfect square? Now again, we have to kind of forget about the negatives right now. We're just focusing on each term. Is 9 a perfect square? Yeah, it was one of our perfect squares. We had 1, and then 4, and then 9, and 16, and 25, and 36, and on and on and on. And 9 is a perfect square, so the square root of 9 is 3. And we have the same binomial here. So everything is a perfect square in this binomial, and everything is a perfect square in this binomial, okay? And so the answer here, if all terms, all parts are perfect squares, if the answer is no, we're done, because to be a special case, if you haven't figured this out, spend all this time talking about perfect squares, to be a special case, you have to have perfect squares in all your terms, okay? All parts of those terms. That's what's going on right here in this, okay? And so, yep, if it's no, we're done. Yes, we move on. So we move on. Now you have to ask yourself the next question. We're going through our special case inventory. Is this binomial the sum of perfect squares? Sum means you're adding them. A squared plus b squared. That chart we did in the beginning, I told you to take a note on. It was written up here, but you know I can't keep everything on the boards and take care of you, so you have that written by your side right now. Or is it the difference of squares? Meaning that in the binomial are the two terms being subtracted. And so you can see here, it is not the sum of squares. If it was the sum of squares, you'd be done, because the answer would be prime to further factoring, okay? Now I want you to understand something here. Okay, everybody, look up here, okay? So what I'm saying is, if this was plus and plus, this would be the answer. Prime would not be the answer, because prime, if you remember, means unfactorable to all methods. Prime means it's totally unfactorable. Please listen to this. We just factored this fetching thing and got this, so it's not prime. The answer, though, is finished right here because it's prime to further factoring. It's prime to the special case method if they're pluses. But if they're minuses, okay, which they are minuses, all right, now we can move on, okay? Because it says, if it's yes to sum of squares, you're done. The answer is prime. But if it's yes to difference of squares, we move on to this step. And this is what I was doing with you on the previous problem that I hadn't written out for you. We sang the little song, okay? So I want you to get this. If the first term is a squared, and the second term is b squared, so a squared and b squared, what we have to do is, we have to take the square root of the first term, okay? So basically, I'm going to rewrite this for you, okay? So we're going to take the square, well, I'm going to write this. We're going to take the square of the first term, and we're going to take the square of the second term, okay? And we're going to get an answer. And we're going to put those answers into a sum and into a difference. So we come back to this, and we say, okay, what's the square root of b squared? It is b. What is the square root of 9? It is 3. And we sing it, Hallie. 1, 2, 3. Put it in a sum, put it in a difference. So there's putting it in a sum. There's putting it in a difference. And that just takes care of that binomial. But this one's the exact same. And so again, we're going to take the square root of b squared, and we get b, and the square root of 9, and we get 3, and we're going to sing it, Hallie. 1, 2, 3. Put it in a sum, put it in a difference. And that, my friends, is the final answer to that problem. Okay? So, what I want you to do right now, go ahead and write all this down in your notes. Okay, it's going to be a little task, and then I'm going to come back after you do that, and I'm going to have a bunch of new problems up here for you to do. Go ahead. All right, can you see me in the video, Hallie? Can you see me over here in the corner?
No.
No? It's just my voice. Can you see all the problems on the board?
Yep.
Okay, cool. All right, you guys, I'm ghosting you, but you can hear me. Woo-hoo! So there are 6 problems on the board up here. And, you know, if you want to pause and you want to tackle these, you can. But I'm not going to pause. I'm going to just jump right in and do these problems with you. So if you're like, I'd like you to help me, Brother Rich, but I think that it would be cool for you to at least try to do some of these. And then all those steps that I wrote, I would keep those beside you, okay? Let's do this first one. Hallie, keep an eye on things and tell me if we're writing off the board here, because I don't want anybody to not see what's going on.
Okay.
B to the 6th minus 9, okay? All right, everybody, we have a binomial, and so we can move on. And by the way, everything up here is a binomial, so we can practice special cases. And so the next thing is, are all my terms perfect squares? We're going to check for that. Is B to the 6th a perfect square? So if you got caught up in the treating 6 like a big number, then you're like, yeah, no, it's not. But it is, because it's an even exponent. And so the square root, and by the way, is 9 a perfect square? It is. If one of them wasn't a perfect square, we would be done. Now we ask, are we adding them or subtracting them? Because if we're adding them, we're done. But if we're subtracting them, then we can go to our next step, which says we take the square root of b to the 6th, which is b to the 3rd, and the square root of 9, which is 3. And Hallie's favorite part, let's sing it. 1, 2, 3. Put it in a sum, put it in a difference. So you take these exact same terms, b to the 3rd and 3, and you put them in a sum, and you put them in a difference. Can we see all that in the camera, Hallie?
Yep.
Okay, great. All right, cool. Let's go to the next one. 4b squared plus 9, okay? First thing, do I have a binomial? Yes. If I didn't, I would be done because special cases can only be binomials, okay? Next thing, is everything a perfect square? Is 4 a perfect square? Yes. Is b squared a perfect square? Yes. Is 9 a perfect square?
Yes.
Yes. Okay, good. Next thing, if you tried this at home and you took the square root of 4 and got 2, the square root of b squared and got b, and you had 2b, and the square root of 9 and you got 3, and you put it in a sum, put it in a difference, well, you wasted a lot of time because the answer to this problem is prime. And the reason it's prime is because that next step was, do you have the sum of perfect squares or the difference of perfect squares? So over here we have the difference, here we have the sum, and because it's the sum, it's prime, okay? Now, can I pause this, the process here for just a minute and explain to you? I get students sometimes, they say, Brother Rich, why is the sum of squares always prime? Okay? So, let's think about this for just a minute. If I have x squared plus 9, do you all agree with me x squared is a perfect square? Yeah. And 9 is a perfect square? Yeah. And so, if we take the square root of x squared, and we get x, and the square root of 9, and we get 3, and you say, Brother Rich, what if I just said x plus 3 times x plus 3? Okay? All right? Well, let's multiply that out. Okay? So let's do this. If we say, oh yeah, put it in a sum, put it in a difference, well, here's the problem. X times x is x squared. X times 3 is negative 3x. 3 times x is positive 3x. Wonderful. Those cancel out. Gone. But positive 3 and negative 3 make negative 9. Okay? Now, positive times that negative makes it negative. It doesn't make it positive. One of the reasons we put it in a sum and put it in a difference is because if we don't put it in a sum and a difference, the middle terms won't cancel out and we have a trinomial. Remember, factoring will always give us an answer that we can multiply back and get the original problem. You know, you take this problem right here. Can you see this, Hallie?
Yes.
b to the 3rd times b to the 3rd, everybody, is not b to the 9th, it's b to the 6th because we add the exponents. b to the 3rd times negative 3 is negative 3b to the 3rds. Positive 3b to the 3rd when we multiply those two, and 3 times negative 3 makes negative 9. These cancel each other out. We have b to the 6th minus 9. Whoa, it's magic. We have the original problem. Okay? But here, what I'm sharing with you is x squared minus 9 does not give you the original problem. So then students will say to me, well, Brother Richie, okay, what if I then did x plus 3 times x plus 3. Well, now your middle terms won't cancel out. Genius. X times x is x squared. X times 3 is plus 3x. 3 times x is plus 3x. 3 times 3 gives you the positive 9 that you wanted. But the problem is that these make plus 6x plus 9, you know, and now you have a middle term, and it does not make the original problem. Then I'll get somebody saying, well, what if I do minus for each one? All right, genius. We'll do that too if you really want us to. Okay. All right, x times x together give you x squared, and x times negative 3 gives you negative 3x, and negative 3 times x gives you negative 3x. Again, a problem because those will combine and not cancel. This does give you positive 9, negative 3 times negative 3, which is what you want, but the problem is this does not equal that. So the sum of squares is prime because of what I just explained, all right? If you don't like that explanation, we talked about this once before, sometimes the explanation confuses you, just memorize it. The sum of squares is prime. Let's move on to the next one, okay? Okay, do I have a binomial? You fetch and betcha. Woo, sounded like a swear word almost. Woo, you fetch and betcha. Woo, say it 10 times fast, you might swear. Square root of 16, I'm sorry, let's back off for a second. Is this a binomial? Yes, move on. Is 16 a perfect square? Yes. Is x squared a perfect square? Yes. Is 25 a perfect square? Yes. Don't worry about the negative right now. When you're talking about is 25 a perfect square. Now everything is a perfect square, so we can move on. Is this the difference of squares? Yes, if it was the sum, we would be done. It's the difference, so I take the square root of 16, which gives me 4, and the square root of x squared, which gives me x, which is 4x. Remember, this is one term, and I can take the square root of the number and the square root of the variable and get this one term right here. And then the square root of 25 is the second term, that is 5. Sing it, Hallie, 1, 2, 3. Put it in a sum, put it in a difference. Boom, and you're done. Kind of cool, kind of fast. You're going to like this section. At least part of it, it's going to go fast. We'll talk about why I say part of it here in a minute. P to the fourth minus 12, okay? Let's look at this problem, okay? Do you have a binomial? Yes, okay, so we can move on. Is everything a perfect square? Is p to the fourth a perfect square? Yes, it is, okay? P squared times p squared. Is 12 a perfect square? No, it's not, okay? You know, we talked about this, 1, 3, not 1, 3, sorry, my bad. 1, 4, 9, 16, 25, right? So 12 falls in between these. It's an imperfect square, all right? And so this is prime. And hopefully you got that right because that's not a perfect square, okay? Doesn't matter the difference of terms. It has to be the difference of perfect squares. So we come to this problem right here, okay? And hopefully you're on top of your A game here. So I bet some of you, if you just got this, you're looking at this and you might have called this one prime. It's not prime. Okay, let's do this problem real quick, okay? First thing, because you might be looking and go, oh, 2 is not a perfect square. Okay, but here's the deal. The first thing we do in every problem, we go back to this. So we've been focusing really heavily on this whole special case thing. But there's a common factor in this, and it's 2. So we put this over 2, we put this over 2, and we get p squared minus 8, okay? Check that out. Okay, now, is p squared a perfect square? Yes. Is 8 a perfect square? No. Okay, and so if you thought it was a perfect square, there's no number times itself that makes 8, and so you're done. This isn't prime it's just prime to special cases. The answer is not prime because you were able to factor out a 2. This is the final correct answer, okay? So we have to still always remember that we're cancer doctors and we're approaching the patient, the polynomial whole and looking at everything, pulling out a common factor, grouping, trinomial methods, and then checking for special cases. And so we did have a common factor here. Let's do this last one. This one's kind of fun for those of you who are weird like me, okay, and like math. Okay, Hallie, take a look and make sure that we aren't writing off the edge of the board here. So maybe we should check for a common factor. Yeah? Is there a common factor? No. Okay, so I didn't remind you to do that on these problems. I kind of did it on purpose to see if I could trick you here. So if I tricked you, yeah. If I didn't, good job. All right? All right. So on this one, do we have a common factor? No. Do we have a binomial? Yes. And because we have a binomial, we can move on. Okay? Is b to the fourth a perfect square? It is. Is 1 a perfect square? It is. Okay? So we take the square root of b to the fourth and we get b squared. And the square root of 1 and we get 1. Okay? And these are the subtraction of, perfect squares. And so we're going to sing our song right now. Go for it, Hallie. 1, 2, 3.
Put it in a sum,
put it in a difference. All right, cool. So we have b squared plus 1 times b squared minus 1. And if you got that right, you didn't get it right. Because, check it out. So is b squared a perfect square? It is. Is 1 a perfect square? It is. Here's the sum of them, b squared plus 1. So that is prime to further factoring, but this is the difference of perfect squares. So we're going to take the square root of b squared, and we're going to get b, and the square root of 1, and we're going to get 1, and we're going to sing it. Hallie, 1, 2, 3. Put it in a sum, put it in a difference. These problems remind me of Russian nesting dolls. Okay, have you ever seen those before? One little doll fits into another doll, fits into another doll, right? And so you've got, this b to the 4th minus 1 makes this, and then this one drops down, and then this fits into it, and so you just keep on opening up those Russian nesting dolls. This is a really good mix of stuff you're going to see in the homework. Let's go ahead and pause. Hey guys, we are back. So I want to talk to you now about your homework assignment, section 5.5. So again, a reminder, we skipped 5.4. And when you get into Canvas and you look up your assignment, it'll outline what section 5.5 is. Please listen, I'm not going to write your assignment on the board here today. To be honest with you, I don't have it with me, and it's not a cut and dry assignment. Please listen, I'm trying my best in section 5.5 to not give you too much work to do. And so there's some areas where I skip some problems for you. There's some areas where I go odd, some areas I go every other odd. So take a look at that in Canvas, and it's explained to you what your assignment is tonight. But in part A of the homework, they ask a question. It says, is the following a trinomial square? It's kind of a crappy question if you don't know what a trinomial square is, so we need to define what a trinomial square is. Hallie, can you see all this in the camera? Will you double check on that for us?
Yeah, we're good.
Oh, all right, cool. All right, camera girl, thank you. So, Hallie's cute, man. She's back there smiling, she's cool. She really digs the put it in a song, put it in a different song. She's been singing it, in between pauses, and so we're going to have a heck of a time, tomorrow, in sacrament meeting at home, because we're doing it at home, She's going to be thinking of put it in a song, she's going to be singing that during the sacrament hymn. That's terrible. Okay, check it out. Trinomial square, okay? A trinomial square, the problem starts out as a trinomial. So these are all trinomials. But after you factor the problem, it ends up as a binomial square because the binomials are going to be the same. Okay? So let's factor this first one, all right? And these could be method 3 or method 4 trinomials, any trinomial. It's just once you get done, the binomials need to be the same for the answer to be yes. And so we say, yep, C equals 64, B equals negative 16. You could do this at home if you wanted to. You could pause and do both of these and factor them. But we have 8 times 8 makes 64. That makes positive 16. Negative 8 and negative 8 make positive 64. When added together, make negative 16. Okay, and we know we're going to take x squared, call that an x and an x, because that needs to make x squared. The negative 8 and the negative 8 drop down. These binomials are the same. Absolutely. And so we could call that x minus 8 quantity squared. So the question was, is this a trinomial square? A resounding yes. Okay, that one is. Okay, now we do this problem right here. X squared minus 14, x minus 49. Okay, C equals negative 49, B equals negative 14. This one can kind of stump you. 7 times 7 is 49. Okay, and that does make 14, but here's the problem. We need 7 times 7 to make negative 49. That doesn't make negative 49. Negative 7 and positive 7 is the only thing that can make negative 49, or positive 7 and negative 7. But when added together, that makes 0. And so this is prime. And because it's prime, the answer is a resounding no, because it's prime. And then I'll get students and they'll say, so if it's factorable, it'll always be a trinomial square? And if it's prime, it's not? No. Please listen, okay? Prime means, obviously, the answer is not going to be a binomial squared at the end, and so the answer is no. But let's take another problem. Let's take x squared minus 5x plus 6. Let's factor that, okay? We factor it, C equals 6, B equals negative 5, okay? 2 times 3 makes 6, when added together makes 5. What about negative 2 and negative 3? That makes positive 6, when added together makes negative 5. Okay, so we have parentheses, parentheses. This is going to be x and minus 2 and minus 3. So this is not prime, but it's also a resounding no. Okay, it is not a trinomial square because the parentheses didn't end up being the same. Let's go ahead and pause that. Okay, so one thing I want to bring up with you before I erase this board is that you have a question on the Chapter 5 test, at least one, if not two, where they ask you, is the following a trinomial square? So you do need to know this concept, all right? Let's go ahead and hit pause. Okay, guys, one of the things that's kind of annoying a little bit about section 5.5 is that while special cases are all binomials, the first part of this assignment really focuses on trinomials, part A and B. So the first part A we just discussed is the following a trinomial square, and you know how to do that now. And then part B, the directive is to factor completely. And I got to tell you, that is the direction on a number of problems on the Chapter 5 test. Factor completely, as soon as you see that word completely, you should write down on your paper the 5 method, your scratch paper, the 5 methods of factoring with the polynomial that they're possible on. Because completely means you got to check for every possible method you can use. I want you, and they say, one other thing, they tell you to remember the common factor. Now on the test, they're not going to remind you that, but they're saying, hey, don't forget to check for a common factor. And then they tell you to multiply to check your answer. What great advice. Every problem you do in factoring, if you're taking a test, you can take that binomial times that binomial or whatever you've got remaining after you factor something out, and you can multiply it back out and see if it makes the original problem. We've been doing that throughout this chapter, and so what I want you to do right now is I want you to go ahead and factor these 3 problems. I'm going to tell you right now, none of them are prime, okay? I'm going to tell you right now that, you're going to need to be cognizant of a common factor in at least one problem up here. And those are more hints than you deserve, right? You're tougher than this, is what I'm saying. You can handle this. So I want you to pause and do these problems, and we will return. Go ahead. Okay, guys, if you remember this method here, you check for a common factor. There wasn't one. We're gonna, I really try to keep these lectures to an hour or less. We're getting close to that hour mark, and so I want to rapidly go through these. And so real quick, I'll just tell you, there's no common factor here. A times C is 4 times 9, which does make 36. B does equal 12. And so we need to find 2 things and multiply together, make 36 when added together, make 12. 6 and 6 do make 36 when added together, make 12. We're going to take this and we're going to break bx up into 2 terms. So we're going to end up with 4p squared plus 6pq plus 6pq plus 9q squared, because this is method number 4. A did not equal 1. And so we got to break this up into 2 terms. 6pq and 6pq do make 12pq. We're going to reorganize this into a binomial plus, always a plus, a binomial. Since that wasn't a minus, I didn't have to take a negative there. I could just do that. The common factor here in this one is 2p. So we put this over 2p, and we put this over 2p, and I'm dropping this answer down here, and I'm getting 2p plus 3q, because these q's cancel out, or so those p's cancel out. The common factor here is going to be plus, because that plus comes along for the ride, a positive 3 and q, and so this is going to go over 3q and over 3q. Q's cancel, 6 divided by 3 is 2p. Looking like we got something working out here. 9 divided by 3 is 3. Q squared over q is q. And so what is cool here is that the common parentheses is 2p plus 3q, and what's left over is 2p plus 3q. Okay? And so I'm going to ask you guys a question. Is this a trinomial square? The answer is yes, because those ended up being the same. You could, in essence, write this as 2p plus 3q quantity squared. Okay? I got to tell you guys, this next one, there was a common factor here. You had to pull out an x. You put this over x, put this over x, put this over x, and you ended up with x squared plus 24x plus 144. This one you could use method 3. This came along for the ride. The x here, c equals 144, b equal 24. We have 12 times 12 makes 144. When added together makes 24. And we end up with x plus 12 times x plus 12. And we could ask, is this a trinomial square? The original problem is not, but this trinomial is a trinomial square because those were the same. You could in essence say this is x times x plus 12 quantity squared. And so we go from there. I want you guys to understand something powerful here. The reason these problems are in this section, look at this, is 4 a perfect square? Yes. Is p squared a perfect square? Yes. Is 9 a perfect square? Yes. Is q squared a perfect square? Yes. I'm going to let you look in your textbook and learn this. And this is nothing to do with time. It is that I never teach these little nuances about this. There's a lot to memorize in chapter 5 with these 5 methods. This is a shortcut that you can take with these 2 methods that I haven't taught you. I'm not going to teach it to you. I'm going to briefly talk to you about it. But these old methods of method 3 and 4 will always work with these problems. But what some people will do is, if they notice that everything in the first term and the last term are perfect squares, then they'll take the square root of 4 and get 2, and the square root of p squared and get p, and the square root of 9 and get 3, and the square root of q squared and get q. And they'll say, well, both of those are positive, so both of these will be positive. And you could say, oh my gosh, Brother Rich, that's so rad. I want to do that every time. Why won't you teach that to us? Well, I'll tell you why. Because there's a lot of factors that make this not work. For instance, the first thing you have to do is you have to look at this problem and you have to say, okay, 4 times 9, you have to take a times c, which is 4 times 9, that equals 36. Okay? And then you have to take the square root of 36, and that has to equal 6. You have to multiply that by 2, and if it equals this, then this problem could work. Okay? So this is the kind of stuff where it's like, I don't know, there's a lot of qualifiers, meaning that this worked nice because you saw me do it first, and then you saw me do it second. Like, oh my gosh, that works. But if that number's not 12, this doesn't work. And the way to know if that number is going to be 12 is that if you take 4 times 9 and you get 36, and you take the square root of 36 and you get 6 and you multiply that by 2, and that makes this number, then this could work. But the other things that say that could work, the other things that have to happen is this has to be a positive to make that a positive and a positive. This has to be, check this out, this has to be a negative and a positive to make that a negative and a negative. Okay, but if that's a positive and a negative, it will not work. And if it's a negative and a negative, it will not work. You can go back and write all those things down. I'm just saying the old methods will always get you there. If you want to learn the shortcuts, you sure can. Because we come back to this, again, is x squared a perfect square? Yep. Is 144 a perfect square? Yep. Square root of x squared is x. Square root of 144 is 12. Plus and plus, plus and plus. You could have dropped down here. So the last one I want to do here with you is we would normally take this if we didn't use a shortcut and say a to the 10th minus 2a to the 5th plus 1. We would then say, okay, c equals 1 and b equals negative 2. Guess what, my friends? Negative 1 and negative 1 make positive 1. When added together, make negative 2. That's nice. Can you see all this over here, Hallie?
Yeah.
Okay, cool. And so we can take this and say, hey, a to the 5th, yeah, that's very good. A to the 10th, right? Because I'm going to have to a to the 5th times a to the 5th makes that. And minus 1 and minus 1. Here's the problem with this problem, is when you look in the back of the book, they say the answer is not a to the 5th minus 1 squared. They say it's 1 minus a to the 5th squared because they use the shortcut. So we go back to this, everyone. Is a to the 10th a perfect square? It is, because it's an even exponent. Is 1 a perfect square? It is. Square root of 1 is 1. Square root of a to the 10th is a to the 5th. This is minus and this is plus, so they're both going to be minus in this time. Okay? And so right now, and this is one of those things where this is a real challenge for people. Okay? Notice that on these ones, it was a plus and a plus, so it was a plus and a plus. Remember, if this is minus a plus, it's minus a minus. But remember, if it's plus and a minus, it doesn't work. And if it's minus and a minus, it doesn't work. And again, we have to say, 1 times 1 is 1, square root of 1 is 1, and 1 times 2 is 2, and so that'll make that work. That stuff can get really tough to remember. So you say, well, if I'm taking a test, Brother Rich, and they say 1 minus a to the 5th, and I have a to the 5th minus 1, I want you to always remember this, okay? They told you to multiply it out. And if you multiply these out, you will get the same answer. So if you see this, and you have this, then my suggestion to you is, you know what? Multiply it out and see if you get the same answer. Okay? a to the 5th times a to the 5th will be a to the 10th. And so if we take this really fast here, let's do this real quick. I'm actually going to erase the previous problem here and show you this real quick. Okay, if we have a to the 5th minus 1 times a to the 5th minus 1, that's going to be a to the 10th minus a to the 5th minus a to the 5th plus 1. Okay, a to the 5th times a to the 5th is a to the 10th, a to the 5th times negative 1, negative a to the 5th, negative 1 times a to the 5th, negative a to the 5th, and negative 1 times negative 1 is positive 1, which makes a to the 10th minus 2a to the 5th plus 1. Look at that. Whoa, it's magic. It's what you rearranged it to be. But if you have 1 minus a to the 5th squared, then you'll have 1 minus a to the 5th times 1 minus a to the 5th. And you'll get 1 times 1 is 1, 1 times negative a to the 5th is negative a to the 5th, negative a to the 5th times 1 is negative a to the 5th as well, and negative a to the 5th times negative a to the 5th, negative and negative makes a positive, a to the 5th times a to the 5th is not a to the 25th, it's a to the 10th because you add them. These two combined, so you have 1 minus 2a to the 5th plus a to the 10th. Well, what's magic? Look at that, you get the one that you hadn't rearranged. And so, I could also, maybe rather than teaching you the shortcut of all those qualifiers, I could tell you this. When you're squaring something, you can rearrange the terms. A to the 5th can come first or last when you're squaring something. Because I've often told you, we've said this a bunch of times, 5 minus 2 is not 2 minus 5. You can't rearrange that. But watch this. You ready for this? If you said squared and squared, they are the same thing. 5 minus 2 is 3. 3 squared is 9. 2 minus 5 is negative 3. Negative 3 squared is 9. That's why you can rearrange those. That is a principle worth memorizing. Not that weird, obtuse, shortcut stuff that was all, if it's positive and positive it works, if you take A times C and, it takes, after you get your product, square root it, multiply it by 2, all that's kind of hard. But this is a neat principle. And the reason it works is because you're squaring this, and squaring a negative always turns it positive, and so those answers end up being the same, right? Because 5 minus 2 equals 3, so this ends up being 3 squared. And this over here, and this is parentheses, this is negative 3 squared. So you're going to, yeah, you get it. It's kind of cool. Guys, part C and D, we've gone over all of it already in the homework. You have an A, B, C, and D. C and D are all the binomial special cases. That was the emphasis of our lecture today. You guys are awesome. I'll see you on the flip side. Hey guys, I'm back. So I told you goodbye, but I decided to do one extra problem here. This will help you. There's a couple problems like this on the homework. There's definitely one of these on the test. And so let's say you're taking the test and you see this and it says to factor completely. First thing you do is check for a common factor. You got to look very closely. You have an even number and an even number and an odd number. So those are divisible by 2, but that's not. The only thing 49 is divisible by, remember that's a perfect square, and you should know your times tables, it is divisible by 7. Guess what? That's divisible by 7. If you remember your times table, 7 times 8. Is that divisible by 7? It is not divisible by 7, okay? That 7 does not go. Hallie and I just looked at each other because there was a big weird sound in here, and it's at night. Woo! Okay. Plus we watched a scary movie the other night that freaked her out, so we're all kinds of stoked. So we checked for a common factor. Why, no, why. Okay, 7 didn't go into this. We checked thoroughly. We had to. We do not have a common factor. You cannot factor by grouping because there's not 4 terms. You cannot use trinomial method where a equals 1 because it just isn't going to work. And because a does not equal 1. So we're going to method 4. And this is going to give you a big, fetching, huge number. So Hallie, get your calculator out, and you're going to be multiplying 16 times 49 and getting us an answer while we figure things out. But just, you get that answer and hold on to it for a second. So guys, if you remember this, if you wanted to take that wild and cool shortcut, I'm going to help you this. Is 49 a perfect square? It is. Is 16 a perfect square? It is. Is y squared a perfect square? It is. So the square root of 49 is 7, and the square root of 16 is 8, and the square root of y squared is y, and both these are positive, and so you could put that just like that, and you would be done and call that 7 plus 8y squared, okay? Which you also know, folks, can be 8y plus 7 squared, because we just talked about that a second ago, okay? We could rearrange that. Either one of those would be correct, okay? But if you don't memorize the shortcut, okay, remember we talked about that's an easy one if they're both plus. Okay, but the other thing was this. Square root of 49 was 7, and the square root of 16 is 4, and 7 times 4 equals 28, right? And 28 times 2 equals 56, okay? And so that's, you know, and that makes that work, okay? If we multiplied those two and it didn't equal 56, then, you know, it's not going to work for us. So, again, I really caution you on this, that you could think something's factorable when it's not, okay? Because if this was 55y or, you know, 25y, it would be prime, okay? It just wouldn't work. So we can always go back to the old method here, where we put this in descending order, 16y squared plus 56y plus 49, okay? And a times c is 16 times 49, and sweet Hallie has an answer for us. What is it?
784.
784. 16 times 49. Double check it, put it in one more time, because we're going to do a lot of work with a really big number here. We've got to make sure it's right. And b equals 56.
Yeah, it's right.
Now here is some great news for you. Do you remember this? These get nasty. We talked about, you know, does our number need to be, you know, bigger or smaller when we take 16 and 49 and we add them together, and that's going to give us, you know, 49, 59, 65, right? And it needs to be smaller, so, you know, our magic pair lies outside or in between. Well, it lies in between is what we're going to say here. But check this out. This is what's cool. If that is a perfect square, and that is a perfect square, go ahead and take the square root of 49. So we say, all right, the square root of 49 equals 7. And the square root of 16, let's find that, and that equals 4. Go ahead and multiply 7 times 4, and that equals 28. Okay? 28 lies in between these two. Try that number. So you say 784, Hallie, and divide it by 28. And you get 28.
Yes.
28 plus 28 makes 56, and you have your magic pair. So one of the things I'm saying is that whole kind of memorizing all of the crap, it can get real convoluted. And again, if this is a minus, okay, and that's a plus, it's going to work, but this is going to be minus here. If that is a minus and a minus, it won't work, and if that's a plus and that's a minus, it won't work. And so just a lot there to deal with that could kick your trash, but this is kind of nice. So now we can take this and say, all right, 49 plus 28y plus 28y plus 16y squared, okay? We can take the original problem, we can break the 28y's up into these two because we're breaking 56y up into this and this. And then we organize this and organize this, okay? And we pull out the common factor. It is 7. We put this over 7, we put this over 7. We get 7 plus 4y. And over here, we're going to pull out an 8y, okay? So we have 8y. And we're going to put this over, my bad. It's not 8, it is 4y, okay? 4 goes into 28, 16. 8 does not go into 28, it does go into 16. So we're going to put this over 4y, we're going to put this over 4y, and we're going to get 28 divided by 4, y's cancel out. 16 divided by 4 is 4, y squared over y is y. Look at that. Our common parentheses is 7 plus 4y. What's left over is 7 plus 4y. And so this and that are the same. What's so interesting here is I've made a fetching mistake somewhere. Oh, you know what I did over there when I did that? And you guys are looking at this whole thing, and while you're watching it, you're like, what the fetch are you talking about, Brother Rich? Yeah, see, look at this. 49, square root of 49 is 7. Square root of 16 is 4. Brother Rich. Okay, and I'm not going to redo this video. I'm going to show you this and let you stew in this and know it's so easy to make mistakes when you're trying to do crap in your head. And that's ultimately where that shortcut method kind of takes you. It can get you a little bit, you know, sketched out here. We knew that square root of 16 was 4. We did that right in here. When we did in our head square root of 16, we got a little ahead of ourselves, okay? All right, you guys, that was just an extra problem. That's one of the ones in your homework. It actually is number 19, okay, number 19. Love you guys. You know, these factoring's a hard chapter. We said that. It's good hard work. Put your heads down. I've got good news for you. We only have a couple more lectures, and the next one is going to be pretty easy. You're not going to learn anything new in that lecture. You guys have a good one. I'll see you next time.